All right, today we're going to tackle a really cool classic problem. It's a fantastic way to get your head around how to move through trees. We're going to figure out how to get the right side view of a binary tree. So just imagine you're standing way over on the right side of a binary tree, looking left. What nodes would you actually see? Well, you'd see the ones on the very edge, right? The ones that aren't blocked by anything else. It's pretty intuitive for us, but how do we teach a computer to see it the same way? So what we're really after is a very specific set of nodes. We need the rightmost node at each level of the tree, and the final answer has to be a list of these nodes ordered from the very top, the root, all the way down to the last visible node at the bottom. Okay, let's look at this example right here. At the very top level, we see node 1, no question. Now look at the next level down. Node 3 is hanging out on the right, and it completely blocks our view of node 2, so we see 3. And at the very bottom, node 4 is the only one on its level that's visible from the right. So our final result is a list, 1, 3, 4. Visually, it's a piece of cake, but coding it, well, we've got two really interesting ways to do it. So our first approach is going to be super methodical. We'll scan the tree one level at a time. This strategy is called breadth first search, or BFS for short. Think of it like exploring a building floor by floor. You check every room on one floor before you even think about going down the stairs. Now, to make this level-by-level thing work, our go-to tool is a data structure called a queue. And a queue is exactly what it sounds like. It's like a line at the grocery store. First person in is the first person out. It is the absolute perfect tool for making sure we process all the nodes on one level before we drop down to their kids. Let's walk through it. First things first, we take the root node, that's node 1, and we pop it into our queue. Since it's the only node at this level, it's guaranteed to be the rightmost one. So bam, we add 1 to our answer list. Okay, now here's the secret sauce. We process that level, we take node 1's children and add them to the queue. But, and this is the important part, we do it in a specific order. We add the right child first, then the left. This means node 3 goes in before node 2. So at the start of this new level, who's at the front of the line? Node 3. We grab its value and add it to our view. And we just rinsed and repeat. We process the nodes from that second level, 3 and 2, adding their children to the queue. Again, always right then left. This puts node 4 at the very front of the queue for the next level. We add 4 to our view, and that's the last level, we're done. Our final view is 1, 3, 4. It works. So, the whole trick, that big aha moment, is that by always adding the right child before the left, we're rigging the game. We're guaranteeing that the very first node we look at for any given level is always the one we want, the rightmost visible node. All right, let's totally switch gears. Forget that level-by-level stuff. For our second path, we're going to take a deep dive, a plunge, straight down the tree. This is depth first search, or DFS. And we're going to make sure we always try to go right first. For DFS, we're going to lean on recursion. The function is just going to keep calling itself, going deeper and deeper into the tree. And our entire strategy hinges on one simple rule. At any node, always explore the right child before you even think about exploring the left child. This right first mindset is the absolute key. Now here's the real magic that makes this whole thing click. As we travel down, we're going to keep track of our depth. And here's the rule. We only add a node to our answer list if the depth we're currently at is the same as the current size of our answer list. This clever little check makes sure we only add one node per level, the very first one we find. Let's trace this out. We start at node 1, depth 0. Our answer list is empty, its size is 0. Hey, depth equals size, so we add 1. Now we go right. We're at node 3, depth 1. Our answer list has one thing in it, so its size is 1. Again, depth equals size. We add 3. Let's go right again. We're at node 4, depth 2. The size of our list is now 2. It's a match. We add 4. Now watch what happens when we backtrack and visit node 5. It's also at depth 2, but our answer list already has 3 things in it. Size is 3. Depth 2 does not equal size 3, so we just skip it. See? It works perfectly. And that's really the whole idea. Because we are so committed to plunging down the right side first, the very first time we hit any new depth, we are guaranteed to be at that level's rightmost node. Any other nodes on that same level will be visited later, but by then, the list will be bigger and our little condition won't be true anymore. Okay, so we've just walked through 2 completely different ways to solve the exact same problem. They both get us the right answer.
Let's put them side by side and really see how they stack up.
So let's break it down. BFS is iterative. It marches level by level using a queue. Its main trick is adding children in that special right then left order. DFS, on the other hand, is recursive. It dives deep using the call stack. Its cleverness comes from combining that depth check with a right first traversal rule. Two different philosophies, same result.
So what's the bottom line here? Well, first off, both of these solutions are super efficient. They're going to run in what we call O of n time and space. BFS gives you that iterative, very orderly level-by-level approach. DFS gives you a really elegant, often more compact recursive solution. Honestly, neither one is just better. The one you choose often comes down to the specifics of the problem, or hey, just which one feels more natural to you.
And that brings us to a final question to chew on. You now have two powerful ways to see the right side of a tree. So what if you wanted to see the left side? What's the one tiny little change you'd make to each of these algorithms to completely flip your perspective? Give that some thought.